most sensitive point of the aircraft, a necessity, or is it a risky development to free up more storage space on the plane? The next time you board an aircraft, you will finally know what is inside those flapping wings. Loading 320,000 liters of fuel into an airplane is both madness and a necessity. The weight of the fuel alone equals 256 tons. This is like having 8 emptied Boeing 737s resting on top of the wings of an Airbus A380. The aircraft's maximum takeoff weight is around 575 tons. 256 tons of fuel makes up almost 45% of this takeoff weight. The maximum landing weight is approximately 391 tons. The difference between the aircraft's takeoff weight and landing weight represents the amount of fuel that must be consumed during the flight. This means that approximately 170 tons of fuel are consumed by the aircraft on a long flight. Thanks to airplanes, the fastest mode of transportation, we can easily travel to the other side of the world. However, this certainly comes at a cost. Aircraft weighing tens or even hundreds of tons result in significant fuel consumption. While the Boeing 737 consumes 2,750 kilograms of fuel per hour, the Airbus A380 consumes approximately 12,500 kilograms of fuel per hour. It is an old paradox that planes, which stay in the air for hours to travel long distances, must carry a serious amount of fuel. If the aircraft is lighter, it can fly further. But in order to fly further, it must increase its weight by carrying more fuel. Throughout aviation history, the biggest problem that has kept engineers awake at night has been where to store the fuel needed to stay in the air for longer periods. In those old and cumbersome designs produced in the past, fuel was stored just under the fuselage or in crude tanks hung outside the wings. However, that ruthless force called wind resistance pulled the aircraft backward with every excess added to the outside, causing it to consume more fuel. If you turn the inside of the fuselage completely into a giant fuel tank, there would be no room left for passengers or cargo, and the flight would commercially collapse. By the late 90s, humanity had begun to dream of taking many more people much further in a single trip. So why aren't the tanks inside the main fuselage the most robust part of the airplane? You might also think that placing the weight of this serious amount of fuel at the bottom of the fuselage would result in a better center of gravity. When you understand why fuel is stored in the wings, it will make perfect sense to you. When the airplane takes flight, all the load is on the wings. In other words, the things that keep that main fuselage in the air are the airplane's wings. Placing fuel, which is almost half as heavy as the aircraft, inside the fuselage would place a serious load on the wings and the connection points of the wings to the fuselage, while the wings push downward with the weight of the fuel inside them. Aerodynamic lift pushes them upward, and these two forces cancel each other out magnificently. The wing, along with the weight of the fuel inside it, fights gravity on its own. When the aerodynamic lift is greater, the airplane begins to fly. If the massive weight of the fuel were in the fuselage, the wing might be able to lift itself more easily because it is lighter. But while trying to lift the much heavier fuselage, the wing connection points could snap. This is the primary reason why fuel is stored in the wings. Of course, this is a much more difficult technology than it sounds. If you were to design the inside of the Airbus A380's wings like a single, completely empty, giant swimming pool, what would happen on the first takeoff would be an absolute tragedy. Imagine that you are carrying a wide, open basin full of water in the trunk of your car, and you suddenly brake or take a sharp turn. All of that water rushes violently in a single direction, instantly knocking over the basin and flooding the entire trunk. This deadly surge, called the free surface effect in aviation, could cause the giant aircraft to flip in the air in seconds when that massive mass of fuel rushes to one end of the wing. When the plane wanted to turn in one direction, hundreds of tons of liquid would pile up in the other direction, and all the control mechanisms in the hands of the pilots would instantly collapse. To prevent such a situation from happening, the inside of the wings is divided into small compartments like a beehive, or the sloshing of the fuel is prevented by a sponge. The same technique is also used in professional drift vehicles. When the vehicles slide sideways, the fuel inside the fuel tank piles up to one side. Since the fuel pump always needs fuel, The gathering of fluids to one side would be a major problem. Therefore, the inside of the tank is divided into small sections, or the fuel is held in balance with a special sponge. Those wings of the airplane are not made of rigid steel or concrete. They move like a living organism. When you travel by a window seat on a plane, you can easily see the up and down movement of the wing. With hundreds of tons of fuel inside, the flapping of these wings actually looks like a terrifying situation. If the engineers had made an inflexible, completely rigid, and hard wing, the wing would try to fight the wind and shatter like glass in the first major storm. Choosing to submit to these massive forces rather than fighting them, the designers allowed the wingtips to bend upward by up to 4 meters during flight. So right now, high in the air, inside those giant wings, there are tons of fuel trying to surge from side to side, and a skeleton bending meters at the same time.